3D space, right? Okay. Let me just draw a Cartesian space there. X, Y, Z, typical 3D space. We always stay in Cartesian coordinate system. So let's say this is X, this is Y, this is Z. Right? What I'm going to do in 3D is very similar to what I was doing in 2D. Always represent the vectors, whatever they are. If they're force, well, in this case, mainly forces. Later on, whatever quantity you're dealing with, there is a vector. Always represent that in Cartesian coordinates. Right? Cartesian coordinate meaning that, well, we have, let me change that. We have unit vectors I along x-axis, j along y-axis, and k along z-axis. Just k is added. As long as you represent vectors using these in Cartesian coordinates, right? The rest is pretty straightforward. Just pretty much do the same thing we're doing for 2D space. Now let's just review vectors in 3D space. Right? Let's say I have a vector here. Let me use this. Let's say I have some. You know what? Let's draw something new. Don't mess with that. So I have a coordinate system. Same coordinate system. I just want to draw a vector there. And this is X, Y, and Z. I will draw, let's say, vector from the other side. Let's do vector A in this way. I'll call this vector A. Now, hopefully you remember, we can just represent this vector with its components along each axis. If I draw this down here, and then we'll get this one this way, and this one this way. So that would be, these are the components. And this is the components. This is another component. This is the third component. Components along x-axis, component along y-axis, and component along z-axis. So the vector A just can be represented. This vector A can be any vector. Obviously, it can be a force. AX in I direction plus AY in J direction plus what do you call it? AZ in K direction, using unit vectors. So the magnitude of the vector was pretty much just the square root of the components in each direction, squared of those components. The angle that vector makes with different axes, right? X, Y, and Z axes, these angles. I'll call this, let me represent it like this. With X, I'll call this alpha. The axis it creates with Y, the angle it creates with Y axis with beta. And this angle, I'll call it gamma. Now in your book, you will see similar procedure or similar way of representing vectors. Instead of alpha, beta, and gamma, you'll get theta X, theta Y, and theta Z, representing angles that specific vector in 3D space creates with different axes. Now those angles, alpha would be, or theta X, let me just put it here, would be cosine inverse of component of the vector along X divided by the magnitude of the vector. Beta or theta Y would be cosine inverse of the component, I should put in parentheses, along Y axis divided by the magnitude of the vector. And gamma or theta Z following the same cosine inverse AZ divided by the magnitude of A. So from there you can also write as long if you know, well, let's put it this way. if you know the components along each axis and the magnitude of this vector, you can find the angles that vector creates with that specific axis. If you know the angle that vector creates with an axis and the magnitude of that vector, you can find the angle, right? Following just the same equation, or using the same equation, you will get AX is equal to magnitude of the vector times cosine alpha. AY is the magnitude of the vector times cosine beta, and AZ is the magnitude of the vector times cosine gamma. And hopefully you remember these from calculus or wherever you dealt with. So the magnitude of the vector, let me just, I don't even know if I should draw boxes around. All these are equations, so let's just go the way they are. So this is how we represent the vector, the relationship between the angles that vector creates with different axes and the magnitude of that vector we can find as long as we have enough information about one another. Finally, we can also represent or we can calculate the unit vector for a vector. So we can define the unit vector. Let me just put here. We can define the unit vector. What is unit vector? If someone can tell me what is the definition of unit vector you have in mind.
Has a magnitude of 1.
Exactly. It's along, if you are defining a unit vector of a specific vector, that unit vector is along that vector, but its magnitude is 1. So if I use UA to define the unit vector of vector A, so UA would be pretty much vector A, was in the same direction, divided by the magnitude of vector A. You can expand this, write it as components of different, different components of the vector A, and that would be I plus AY over AJ plus AZ over AK. So that's the unit vector along vector, unit vector of A, well, unit vector for vector A, that's it. Obviously the magnitude of this is 1, that's the definition of unit vector. But one more thing is, if you look at this AX over A, we defined AX over A here, right? We said if you use or look at this expression, AX over A is cosine alpha, AY over A is cosine beta, and AZ over A is cosine gamma. So I'll just plug them here. So you can represent the unit vector also as cosine alpha I plus cosine beta J plus cosine gamma K. As I said in your book, I think the preferred notation is theta X, theta Y, and theta K, which probably is a better way of doing it. But I use alpha, beta, and gamma. I try to use both, so you know that they both can be used in different texts. But alpha is theta X, beta is theta Y, and gamma is theta Z. So let me just add that here. So this is the unit vector also. This is a vector, so I put the arrow. Now, two things we know about unit vector that can help us to calculate, well, one thing technically we know, but another thing is more about the what we can conclude from that. So we know for a unit vector, the magnitude is 1, so magnitude of UA, not A, is 1. What does that mean? It means that, what is the magnitude of UA? It means I can actually write, well, cosine alpha squared plus cosine beta squared plus cosine gamma squared is equal to 1. Because that's the definition of magnitude, right? Squared root, well, you can put the square root here, but the square root of 1 is 1, so I just squared both sides. So this is also something to remember. Sometimes if we know, well, we are in situations, we are in a situation that we know two angles, right? Two of the angles that the vector creates with different axes, we can find the other one or the third one using this relationship. So why do we define unit vector? Because we can represent the vector with its unit vector. As I said, a unit vector has the same direction as the vector itself, a unit vector of a vector, but the magnitude is 1. So if we multiply that unit vector with the magnitude of the vector, it gives us the vector itself. I know I use so many vectors in one sentence. So let me just do it this way. Vector A, do it this way, can be represented as, if this is A would be the magnitude of A times the unit vector for A. So pretty much that'll be, if I expand it, cosine alpha I plus A cosine beta J plus A cosine gamma K. Just to make it a little less crowded here, well, let me identify the things that are, well, relatively more important. And this one. Let's see, definition of unit vector. Maybe I should do the same for the previous slide. This one, and I would say this one. Although everything here is important, but